Hi, I'm Devin Singh. I'm a computer engineering major.
Hey, I'm AJ Tulsi, electrical engineer major.
Hello, I'm Dave Berlino, electrical engineering major.
Hello, I'm Bobby Federici, electrical engineering major. Our project is HeatSquared. That stands for Heat Emitting Automatic Temperature Square. We are building a cost-effective way for homeowners to melt their driveways and pathways when snow falls on them so that ice does not accumulate.
This is the current reading of the temperature and humidity for our project. The current house temperature is 76 degrees with a humidity reading of 48%. So this is our negative temperature coefficient thermistor. It's a 3950. The thermistor has an error range of plus or minus 5 degrees Fahrenheit. And this is our DHT11 humidity sensor. Our DHT11 humidity sensor has an error range of 10 to 15% error. This is currently our breadboard configuration for our project. We have the Mega chip popped in here so that we could flash code to it and read in serial in real time what the temperature and humidity sensor are currently reading. Both of these values are within an acceptable range.
This is our truth table for our sensors and our relay. If the humidity and temperature sensor do not meet their thresholds, the relay does not kick on and the LED shows as white. If the temperature sensor is the only one that meets the threshold of the temperature and humidity sensor, it turns blue. If it's only the humidity sensor that meets the threshold, it turns green. And if everything is working correctly and the relay kicks on, it turns red.
All right, so as you can see from our truth table right now, the LEDs are red, which means that both sensors are active. The way we tested that is we have our temperature sensor inside of a cup of ice, and our humidity sensor, because we live in Florida, is above the threshold that it needs to be. As you can see, this relay has a red LED showing that it is on, which turns on this lamp right here. We've got this lamp as a placeholder instead of the heating cable for now. Now, when I take this humidity sensor and unplug it, we are going to get a blue LED, which, as you can see from the truth table, means that the temperature sensor is meeting its value and the humidity is not. That also turned off the light. When I plug this humidity sensor back in, it will go back to red because the temperature sensor is meeting its value, and then this will in turn turn on the light. Then I take this temperature sensor out of the ice and I hold it between my fingers for a couple of seconds. It will turn green, which means that the humidity sensor is meeting its value, temperature sensor is not, light has now turned off. The last part of our truth table is the humidity sensor being unplugged. The light will turn white, and now this shows that both of the sensors are not meeting their thresholds.
So this is going to be our heating cable. This is 43 feet long, which when coiled will give you about 10 feet. Our enclosure is only going to be a 1x1 square, so we will not be using the full 43 feet here. The resistance reading for this heating cable is 28 ohms, which would get us 500 watts when 120 AC power is applied to this.
This is the HeatSquared fully assembled. It is constructed strictly out of wood, which acts as a great heat insulator. The middle channel of the HeatSquared has a protective plexiglass that covers the LED strip, which gives the user the operational mode of the unit. In the same cavity, we will surface mount the temperature sensor. It is not surface mounted in this demo for testing purposes. We need it long enough to put into a cup of ice to meet the temperature requirement of the HeatSquared for it to activate. The outer channels are where the heating cables run. Under the pavers, we can see the heating cable compacted with foundation sand. This will help the heat transfer from the cables to the surface of the pavers. The entire unit is sealed with a high temperature silicone bead that runs all through the cracks of the HeatSquared. This will prevent water and any kind of debris from entering into the electronics cavity, which is also separated from the heating cables. We decided to go with a drawer style electronics cavity for multiple reasons. One being easily accessible, that all parts can be tested and serviced without taking the entire unit apart once sealed. Let's take a close-up look at the electronics cavity. In the very front of the unit, we have a waterproof 120 volt AC electrical inlet This adds the convenience of plugging in this unit as any standard electrical device using an extension cord. Once power enters the HeatSquare, it feeds to a distribution block by a line, neutral, and ground. One line wire goes from the distribution block to the relay and waits for activation, while a line and neutral from the distribution block goes to the AC to DC converter. This outputs 5 volts to feed to the PCB through this connector. Once the PCB is powered on, it begins to read a signal from the temperature sensor through this connector, the humidity sensor through this connector, and outputs the state of the HeatSquare to the LED through this connector. Lastly, this connector powers the relay, and when all conditions are met, outputs a signal to activate the relay, which sends the line power back to another port on the distribution block that is connected to the heating cables. These 3 wires come from the heating cable. One goes to line, one goes to neutral, and one goes to ground on the distribution block. So this is the final demonstration of the HeatSquare. We're going to run a time-lapse video to show a heated paver versus a non-heated paver. The top of the screen shows a non-heated paver, which reads about 78 degrees, and on the HeatSquare itself, the paver reads about 103 degrees. We have the temperature sensor in a cup of ice, which reads 30 degrees. We're now going to put some blocks of ice on the HeatSquare and the non-heated paver and show the differences.